We're at the top of page 13, beginning of the chemical math unit, and this unit sounds a lot harder than it really is. You're going to need a periodic table in hand, so we can start with some formulas. And we'll begin with the formulas of binary compounds. A binary compound is a compound that consists of only two elements. For example, this one here, sodium and oxygen forming sodium oxide, or calcium and nitrogen forming calcium nitride. Now, to get the ratio of the elements in the compound, what you need to do is first find the oxidation states of these elements, which are the charges that are to the right of the elements in your periodic table. And then you crisscross the oxidation states. Of course, write the positive one first, followed by the second, which in this case here would make sense. It's a metal and a non-metal. The metals form positive ions and the non-metals negatives. And then what you do is you simply crisscross, you switch, if you will, the oxidation state, so that 2 drops down to here, and that 1 drops down to there, except we don't write the 1 is assumed. All right, and we end up with Na2O, which simply means that there are 2 sodiums, the +1 charge, and 1 oxygen, 1 oxide ion in this compound. And notice how you end up with the right ratio, and that gives you a neutral compound. Positive 1 is a +2 total, and that would balance the -2 of the oxide ion. Also notice that we drop the ending here of the oxygen, and we change it to IDE, which is a typical ending of binary compounds. All right, so. And that would be changing the ending of the second element to IDE. If you move along to calcium nitride, you'll notice that nitrogen has a lot of oxidation states. In fact, more than I have listed here. Nitrogen is a non-metal, and in that case, when you come across non-metals with multiple oxidation states, then you simply choose the top one. So in the case of nitrogen, its nitride ion, its most common would be the N-3. And again, you just crisscross, and you end up with Ca3N2. And let's check again how that gives us the ratio for a neutral compound. So there's 3 calcium ions, giving you a total of +6 charge, to 2 nitride ions, giving you a total of a -6 charge. And as expected, you have a neutral compound. So that's what crisscross does for you. It gives you the proper ratio to give you a neutral compound. And again, the subscripts indicate how many there are of each element, how many atoms of each element, or ions, better said, in these compounds here. All right. Again, I say crisscross, drop the signs, that is the positive and negative signs, and simplify. Sometimes you come up with a ratio that has to be simplified. For example, let's say you had x, which stands for any element, x +4 and y -2. When we crisscross these, we end up with x2, y4, and clearly this could be simplified further to x, y2. So it's crisscross, and you have to simplify after you've dropped the signs. All right, so that covers the binary compounds. And then let's turn our attention to Table E with the polyatomic ions, because the same thing occurs there. Remember, polyatomic ions are many atoms having 1 charge, many non-metal atoms having 1 charge. So the other thing about Table E with the polyatomic ions, you just want to be careful to include, to write in the proper charge, and also to not confuse the 8s with the ites. So here we have barium nitrate, ATE, versus barium nitrite, ITE. And that's the difference between an NO3 and an NO2. So again, what you do is for the barium, list that one first since it's the positive ion. The nitrate ion, it says there in table E just a minus. It's assumed that you know that's a -1, but I'll write it in here for teaching purposes. So leave these numbers alone, that is the subscripts of the poly, and just again crisscross the oxidation states or the charges. And here you'll have BaNO3 You're going to write a parentheses around the NO3, the nitrate, because you need 2 nitrates to balance the barium. So to break that down, that means Ba plus 2 and 2 nitrate ions with a -1 charge give you a neutral compound. And then here, barium nitrite, same operation, except that it's an NO2 instead of a NO3. And again, we use parentheses when there's more than one polyatomic ion. If there's only one polyatomic ion, as in the case of, let's say, sodium nitrate, well, there's no need to use parentheses there because there's only one of them. So if you need more than one, as in the case, let's say, of aluminum nitrite, AlNO3, that would mean you need 3 nitrates to balance an aluminum ion. All right, so that's pretty easy. Why don't we try doing one together now? I'll give you a chance. How about you do magnesium acetate? Magnesium acetate. Let me get a better marker while you work on that. Magnesium acetate. Hopefully this one is better. All right, so you look up the magnesium, which is your metal ion in the periodic table. Magnesium is Mg and has a charge of +2. That's better. And the acetate, if you look at the polyatomic ions, many of them end in -ete or -ite. The acetate ion can be written in a couple of ways, actually 2 ways, as C2H3O2-, or if you want to emphasize its organic aspect, CH3CO-. But let's use the first one there. So it's C2H3O2-, and of course it's -1. Let's crisscross again. We get Mg, parentheses, because we'll need more than one, acetate ion, and put a 2 there. That's the key there, putting the 2 outside of the parentheses, indicating that you need 2 acetates to balance the magnesium. So that's pretty simple. Now what I want to do is, I want to look at the transition elements, which I mentioned in the periodic table, unit, that for the transition elements, or metals that have more than one oxidation state, we indicate what the oxidation state is and the name of the compound. So let's drop that down and go over that again, because in periodic table I mentioned it as something that's tested, but I did not elaborate there. So why don't we find iron first of all, in the middle of the table. Iron is element number 26, I believe. Let's double check. It's in group 8, element number 26. Iron, you'll notice, has 2 oxidation states, so we're talking about, again, the transition elements or metals. Those multiple oxidation states. And the ion can either be an iron +2 or an iron +3. Now which one we use depends on the compound that you intend to make. And iron Roman numeral 2 would be iron with a +2 state. Iron Roman numeral 3 would be iron with a +3 state. So in other words, the Roman numeral is the actual oxidation state. So even if you had something like Mn, which has oxidation state of 2, 3, 4, and 7, the Roman numerals would be 2, 3, 4, and Roman numeral 7. So it's the actual oxidation state, not the order in which the oxidation states appear. Many times students think that the +2 means it's the second oxidation state. No, it's the actual charge of +2. It's the actual oxidation state, not the order. And so again here, when we crisscross and simplify, it would be Fe2O2, which simplifies to FeO. And here you get Fe2O3. Notice how I drop them down, and notice how I get rid of the signs. Now if you had to go backward on this, if they gave you this compound and they asked you to name it, when you work it backwards, remember the first has to be positive, so it would be chromium plus 3. So I'm actually doing the reverse of crisscross or cross-criss. The second ion would be negative, and since the chromium has more than one oxidation state, in fact, the chromium, if you look it up, the chromium could be a +2, +3, and a +6. So having more than one oxidation state, you'd have to indicate here that it's the chromium +3 oxidation state in the name of the compound. And without that Roman numeral, it would be wrong. All right. Why don't we try combining all of this now, and let's do a polyatomic ion with a transition. So why don't we do nickel 3 chlorite. Okay, so I'll write it down here. Nickel 3 chlorite. Again, that ITE is telling you to go to table E, look up that polyatomic ion. The nickel 3 is nickel +3. The chlorite, not to be confused with the chlorate or the others in that series, is ClO2 -1, of course. Then when you crisscross these, you end up with Ni parentheses ClO2 3. Right, so I'm running out of space here, so let me write it over here. Ni parentheses ClO2 3, indicating that there's one nickel ion and 3 chlorite ions there necessary to form a neutral compound of these two. Okay, let's continue. That's pretty much it on formula writing. Let's continue now, just breaking down once again, understanding what the formulas mean. And that is, let's start counting atoms. All right, it says here, finding the total number of atoms per unit of compound. Suppose they give you AlClO33 and they ask you, in a unit of this compound, what is the total number of atoms? That is, all of the atoms. Well, you're going to have to distribute this 3 here to get rid of the parentheses. All right. And so here you'll have 3 times 3, 9 oxygens, and 3 times 1, 3 chlorine atoms. But 3 does not apply to the aluminum. There's only 1 aluminum. So it's 1 aluminum, 3 chlorines, and 9 oxygens is going to give us a total of 13 atoms. Now this may seem a little confusing when we look at hydrates and they ask you to add up the atoms. Remember, a hydrate is a salt that has water attached. So it's a salt with H2O attached or bonded to it. Remember, salt is an anionic compound. So here, to indicate that the water is attached to copper sulfate, they add a dot. But that dot doesn't mean to multiply. That dot means to add, that it's been added to the copper sulfate. So in this question here, you're asked to find the total number of oxygen atoms. So we have 4 oxygen atoms on this side, plus 5 waters, which are really 5 oxygen atoms on that side. So 4 and 5 would give you 9. If you wanted a picture of this, what I'm saying is the CuSO4 has 5 waters attached to it. Whatever that arrangement is, is the material. There you have it, the 4 oxygens and the 1, 2, 3, 4, 5 around it, giving you a total of 9. Of course, there's some kind of attraction here that's bonding the water to it. Now, if they were to ask you, instead of finding the total number of atoms, they were to ask you what is to find the moles of atoms, well, it would be the same answer. Because remember that the formula represents a unit of that compound, and specifically a mole of that compound. A mole is a certain amount, all right, and which you would get from the gram formula mass, which we'll talk about later. So 9 atoms and 9 moles of oxygen atoms would be the answer to this question. All right, so like I said, the math unit is real easy. And now you need a calculator on the next page, because we're going to do a little percent composition and a mole calculation, but really that's as deep as it gets. All right, let's take a break right here. Maybe you want to go through what we just did, or maybe you want to do some more problems on your own with formula writing. I have some in the back.